So, what might a model of sentence comprehension under uncertain input look like, and what interesting consequences might it have? To try to address this question, we're going to turn to information theory, as we have done a number of times throughout this course, this time to look at the noisy channel theory, which was part of the mathematical theory of communication that Claude Shannon introduced in his seminal work, one of the greatest pieces of scientific and mathematical work in the 20th century, in 1948. On this view, it is productive to look at communication in the following abstracted format. There is an information source from which we get a message which is converted into a signal by a transmitter. It is then sent out and subject to noise in between broadcast and the receipt at the receiver. And then what the receiver does with the received signal is that the destination decodes and tries to obtain a reconstruction of the message that was intended from the information source. So what we're going to do is we're going to basically label the parts of this diagram with parts of the linguistic communication process, and then interpret them according to principles of Bayesian probability. And once again, this is just a very vanilla application of the idea of noisy channel theory together with simple probabilistic principles. On this view, the intended message, of course, there is a prior distribution over that. There is a language production would then give rise to an utterance, and there is a speaker likelihood that governs the likelihoods of utterances given intended meanings. Noise sources affect the utterances. And so what the received signal is we're going to call that signal I, input. And the input will, of course, have a likelihood given an intended utterance, which will reflect all sorts of noise. And then the problem of the comprehender is to reconstruct the likely utterance and the likely intended meaning given the input. What does this mean for sentence processing? On this view, in sentence processing, so for example, if we wanted to do something like parsing, on standard probabilistic sentence processing, if we want to get, for example, like the probability distribution over parse trees T for a word sequence W, we use Bayesian inference and we say that it's proportional to the likelihood of the word sequence given the tree times the prior probability of the tree, or without using the chain rule decomposition, it's just the joint prior on T and W. But if we don't observe the sentence W, but rather a noisy input I, then actually we have to do something a little more complicated. So for example, if we're interested in recovering the intended structure given the input, then we need to marginalize over the possible word sequences that might have underlined that structure. Alternatively, if we want to reconstruct what the word sequence was that somebody said, we'd be marginalizing over tree structures. Once again, we're conditionalizing on the input I, not on the structure T or the sentence W, because neither of those is known. Now, in an experimental context, for example, in the context of understanding with psycholinguistic experiments, understanding noisy channel processing, we would then have a slightly different problem. So suppose, for example, that we wanted to model the comprehender, what sentence they thought a particular sentence was likely to be, but I, the psycholinguist, choose the actual sentence that somebody is reading. So if I know the sentence that is presented to the comprehender, what I don't know is what the input is. The noise processes in that particular instance of comprehension are not manifest to me as a researcher. Rather, I need to marginalize over them. And simple probability theory, the chain rule decomposition, says that I can decompose that to the probability under the true noise source in the world of an input given the sentence that was out there in the world times the conditional probability of what the comprehender might think it would be given the input and the true sentence. Notice that in this model there are two different kinds of models of input and noise. One of them is what we can think of as the comprehender's model. And that will govern the relationship between the hypothesized possible sentence W and the actual input I. The other is the true model. That is, what noise processes exist and how do they modulate the signal or the intended utterance to create an actual input percept of a sentence as a function of that. And we can actually use some Bayesian inference. We can do some clever things. So first of all, notice that if you harken back and think about the last slide, that if you think of that as a graphical model, which is actually a legitimate interpretation, we have conditional independence of W given W star because the comprehender doesn't have access to W star, only to I. And so we can actually cross off this term from here. And then we can use Bayes' rule to rewrite this. So we would say that P sub C of W given I is going to be P sub C of I given W times P sub C of W divided by the normalizing constant. And when we play this out, then we get the following form. So the P sub T term has stuck around, and then the other terms have come out of Bayesian inference on the P sub C term in the upper equation. One of those terms is a prior on W that does not depend on I, so we can pull it out of the integral. And then we get this piece, which I've underlined, which we're going to call Q of W and W star. Effectively, this is what this is going to be doing, is it's going to be scoring this sort of similarity of the actual sentence and the possible sentence that the comprehender would entertain as the sentence that they may have heard on the basis of the input. What this means in practice is that Q is going to be a scoring function that favors sentences that are similar to the true sentence. So it's going to be a pressure that, on average, leads comprehenders to correctly identify the sentence W star. On the other hand, there's this other pressure, which is the prior. So the comprehender inferences then are going to be a balance of, we're going to see them balancing out. Basically, they're going to tend to infer that the sentence was what it actually was, but they're also going to tend to infer that the sentence was something that was a priori probable. Okay, so how do we actually instantiate a model like that? Well, there are a lot of things we have to do. The first thing we're going to have to do is to represent noisy inputs. And we're going to use probabilistic finite state automata to do this. Now, this is actually something that builds on our work with finite state models earlier in the semester. I'm going to give you just a brief overview of what it is and then a formal definition. So here's an example. Let's suppose that we have a language which is vocabulary items A through F. Okay, so there's 6 elements in the language. And this is a little probabilistic automaton. The non-probabilistic part that you can probably recognize that this has 3 states. State 0 is the initial state. State 2 is the final state. State 1 is not a final state. And you can see the arc. So any string that this automaton will recognize will be of length exactly 2. And the annotations on the arcs or on the transitions in this automaton are a lot like the ones that we saw earlier in the semester, but they have a little bit more. So they have an input symbol. That is the symbol that has to be there at that point in the string in order for the input to be consumed and to transition to a new state in the automaton. But then there's something after the slash, which is actually the log probability in this formulation. So that is the surprisal or probability, the negative log probability in base 2 of the actual transition. We can actually think of this automaton. So you'll notice that if you sort of think about being in any particular state, the sums of the probabilities are going to be of the transitions going out from that state are going to be 1, because so log base 2 of 2 is equal of 1/2. Negative log of base 2 of 1/2 is equal to 1. And negative log base 2 of 1/6 is equal to 2.58. So what this is actually saying is that each of these 2 transitions here has probability 1/2. Each of these 6 transitions here has probability 1/6. And so if there's a 6-item vocabulary, this is sort of equivalent to an automaton that represents the knowledge state about an input. The knowledge state that it represents is that the first word in this 2-word utterance, so it's a 2-word utterance, the first word, the first symbol is either A or B with equal probability, and I have no information about word 2. That is, I have a uniform distribution over the second word. Here's a formal definition of weighted finite state automaton. The first parts are exactly familiar from before, they should be. So there's a finite set of states Q, a finite set of terminal symbols sigma, a set of final states, which is a subset of the set of states Q. Q naught is the designated start state, and a transition function, which has the form that you input. If you're in state Q, you can take, and you see symbol I, you can consume it and move to state Q prime. What's new is that we have a function that maps transitions to real numbers, which we can think of as weights. In general, in our applications, the weights will correspond to negative log probabilities, but actually the weighted finite state automaton formalism is even broader. So probabilistic finite state automata are a subclass of weighted finite state automata. And then furthermore, final states themselves have weights as well. And rho is a function that maps the final states to the real numbers. And so given that definition, then the definition of the criterion for a string being accepted or recognized by an automaton is the same as before. There has to be a path that transitions to a final state that traverses the string in question. The weight of the path, then, given a path that accepts or recognizes a string, the weight of the path is the product of the weights of each of the transition together with the final weight of the final state. So if I have all these transitions that I have here, I multiply through all their probabilities or weights, and then I multiply in the weight of the final state. And if, in general, in the cases that I'm going to show you, if the final state does not have an explicitly marked weight, it was going to be 0 or probability 1. Okay, so we are going to use weighted finite state automata to represent uncertain input. It'll turn out, and we can discuss this in greater detail in interactive sessions if desired, that weighted finite state automata are a very natural formalism for many kinds of uncertain input representations. Furthermore, we're going to use a probabilistic grammatical formalism to determine beliefs about which strings are likely to be seen. So the prior in the uncertain input model is going to be a probabilistic grammar of some form. Now, there are many probabilistic grammar types that we could use. We've seen probabilistic context-free grammars, for example. There's more expressive formalisms. For example, probabilistic minimal grammars exist. We're not going to cover them in this class, but they're available. And then there are also probabilistic finite state models. We actually just saw those. For convenience, for the simple examples that we're going to see here, we're going to stick with probabilistic finite state models. But also, there are some bonus slides which talk about how to put together probabilistic context-free grammars and probabilistic finite state models together in a more general way than what I'm going to show you in these main slides here. Those slides are available up on Stellar. So here's a simple example that is this is a toy grammar, but it's interesting for the present purposes. So this is a grammar over the same vocabulary, A through F, 6 items. And what I'm representing here are it's a probabilistic finite state model where, once again, we have the inputs and the these negative log probabilities. And this, you can see, has a bit more different of a structure. As with the first automaton we looked at, every accepted string has to have a length of equal to 2. But notice there's a little more structure, and sort of overall speaking, there's 2 broad paths between this automaton. In this automaton, in position 1, the first transition that you would have from the initial state, you could have any of A through D. They all have negative log probability in base 2 of 2, so that's 1/4 probability, so they're all equally likely. But now in position 2, things get a little more interesting. If I saw A or B first, then I'm in state 1. And if I am, then the lowest surprisal thing to have happen next is that I would see E. I might also see F. Log base 2 of 3/4 is equal to 0.415. And of course, log base 2 of 1/4 is equal to 2. So there's a 3/4 probability of getting E if I saw A or B, and a 1/4 probability of getting F. But if I saw C or D, then it's the reverse. With 3/4 probability, I'll see F, and with 1/4 probability, I'll see E. So that's the formulation here. Now, remember that Bayes' rule says that the evidence and prior should be combined, in particular as probabilities, they should be multiplied. And it turns out that we can use probabilistic grammars in this setting by using the formal operation of weighted intersection. And you may remember that finite state automata are closed under intersection. So you can take any 2 finite state automata over the same vocabulary, and you can intersect them and get a resulting automaton out. And it will accept only the strings that are accepted by both of the 2 automata. When these are weighted finite state automata, you can also intersect them, and you will get out what is effectively the combination of the 2 models. It will only accept strings that are accepted by both automata, and it will put a weight on each string that's accepted, which is the combination of the weights of the 2 automata. And that is a weighted intersection operation. And we can actually even do a normalization step, which turns it back into a probabilistic model, a proper probability distribution over strings. So let me give you an example of this. So here's our input And for technical reasons, we actually use a transducer formalism to do this. And that is what explains the colon. So, but effectively speaking, A colon A in this setting really is the same thing as just A. And so this is our input, this was our grammar, and we can combine these and we get what is a posterior belief state after combining the input and the grammar. And this is exactly what I would expect. That, well, the grammar didn't care, it didn't really prefer A or B in the first position, neither did the input, but the input ruled out C or D. And so what we're left with is in the posterior belief state, it's equally likely the first word was either A or B. Now the input didn't care about position 2. It didn't have anything to say about position 2, but the grammar has something to say about position 2. In particular, if in position 1 you saw A or B, then the grammar tells you that you have to have seen E or F, and you probably will see, you have to see E or F next, and you will probably see E. That's reflected in this new belief state. The additional decimals are simply rounding error in the computational implementation. But now, so what has happened is that we've taken information from the input, and the grammar has propagated that forward into the future. Okay, so you can think of the input representation as having no information, not yet having even seen position 2, but the grammar propagates information about position 2 forward from position 1. And so you can think of this as prediction. Okay. So grammar affecting beliefs about the future, grammar is doing probabilistic prediction. But there's more. When we're uncertain about the future, grammar and partial input can affect beliefs about what will happen. That's nothing new. Really, we've seen this before in expectation-based processing and surprising. What's new is now, because we have uncertainty about the past, grammar and future input can do something different. In particular, they can also affect beliefs about what has already happened. So new future input can actually change your beliefs about the past. To see this, I'm going to take the same grammar as before, and I'm going to take a slightly different input. So first, let's imagine a state which I'll describe as, once again, it says the input has to be 2 words. The first word is either B or C with equal probability, and as before, I have no information about the second word. If I intersect this with the grammar, then I get this automaton, which represents an interesting contingency. I still don't know whether I saw B or C, but the contingency is that if I saw B, then I'm going to see probably E next and maybe F. If I saw C, then I'll probably see F next, maybe E. Now let's imagine that I get future input about, and I subsequently get input about the second word. In particular, I get something that sort of looks like F. That is that the negative log probability, the surprisal at the input representation, is more consistent with F than it is with E. In particular, this is once again log base 2 of 3/4 is equal to 0.415. So this is 3 times as good a match with F as it is with E. Now I'm going to intersect this grammar with this second automaton. And now I get something interesting happening. So it's not as obvious what happens down here. In fact, if you were to marginalize this out, you would find that F would be 3 times as likely as E. But now what has happened, which is very interesting, is that that information has gone back and propagated into the past. And now this equal probable distribution over B and C that I had after seeing 1 has changed, even though I didn't get more input. So there's no change in the input representation for word 1, but there is in the posterior representation. And the reason is that the input from position 2 was more compatible with one possibility for position 1 than it was with the other possibility. And it's grammar that creates those contingencies between parts of a sentence. So we have now a noisy channel model. We've got most of the pieces. We have this expected posterior belief state of the comprehender of W given W star. W star the true sentence, W the possible sentence that the comprehender is interpreting. There's an effective prior and an effective expected evidence or expected likelihood. And then we need one more thing, which is we need to instantiate this model in a way that's scalable. And we'll say as follows, that it's going to be a way to find a state automaton, and we're going to take the true sentence, W star, and then we're going to build something that's based on Levenshtein distance, which is basically the number of character edits that you need to get to one word from another. And that's going to look something like this. So for example, if I take the true sentence, a cat sat, and maybe my, and my vocabulary is simply the empty string cat and set, then my automaton would look like this. Okay, so and the way that I constructed this automaton, as I said, well, there's going to be an arc for every possible input string, every possible input position. So and the cost of no edits is 0, and the cost, really, you can interpret that in log probability space. And the cost of an edit from one word to another is the number of character edits that is required. So changing to cat requires 2 edits, so that's a cost of 2. Changing cat to sat, for example, is a cost of 1, and so forth. We also allow insertions and deletions. So changing cat to nothing costs 3. Changing nothing to cat costs 3. And those insertions and deletions are, in fact, represented and implemented as loops in the automaton for insertions and epsilon transitions for deletions. And so what do we get from this? So for this input, the lowest cost W for this input W star is going to be the veridical interpretation, the W equals W star. So the cost of a cat sat, there are 0 costs for all these transitions. The cost of sat cat, for example, is much higher. It is of cost 8 in this case, because we required an insertion, and we also required some modifications of previous sentences or previous words. And in fact, you can see that there's actually this induces a input representation of an infinite set of strings that is possible. But because via the automata we can efficiently operate on them, we can actually still take this infinite set of strings and intersect it with a grammar and get a tractable distribution to work with. One side note that I'll note, that you'll notice that, well, if we think of 0 as a log probability of 1, this is an improper distribution, but it is still, we can take the expected evidence doesn't itself have to be a proper probability distribution. It just has to be a weighted distribution that is well behaved in a number of respects. So we'll take a pause for a moment, and then we'll come back and see how this can be applied to the example of the coach smile that the player tossed the frisbee.